Hello everyone, this video is going to cover sections 3.5, 3.7 and 3.8. Before we go there, let me just refresh your memory because it's useful to remember a few things. So remember last time we introduced random variables in general. And remember, for any random variable, the notation is going to be the following. Y will be the random variable, so I'm going to be using RB from now on, in lowercase where the possible values for the random variable. Okay. And the properties were the following. Remember, the probability for any value has to always be between 0 and 1. And 2, when you sum all the probabilities, it has to equal to 1. Also, you can call this, I guess, number 3. Every random variable has a expected value, which is denoted for mu. And every random variable also has a variance, which is defined to be the expected value of y squared minus the expected value of y squared. There is another definition, but we will use this most of the semester. Right, so therefore this is the case for any random variable. In section 3.4, we talk about the binomial random variable. And for that one, the density function was equals to, remember, n choose y, p to the y minus p to the n minus y, where y was equals to 0 all the way to n. Okay, so that's what we did last time. In section 3.5, we have a specific random variable called the geometric distribution or the geometric random variable. The definition is the following. A random variable y is said to have a geometric probability distribution if and only if the following is true, meaning this should be the density or the mass function, and y goes from 1 to infinity, which makes this a countably infinite sequence. Here, p is the success probability, similar to the binomial. Therefore, 1 minus p is technically q, and this is the failure probability. Okay. Now, what the geometric distribution actually computes, it computes what's the probability that you'll be successful after the first try, the second try, the third try, and so forth. So for example, if y is equals to 1, then the probability of 1 will be q to the 0 times p, which is just p. That means you were successful in the first attempt. If y equals to 2, then p of 2 means this will be q to the 1 times p, which is just technically q times p. And this means you failed the first time, but you were successful the second time, and so forth. Okay, so let's do one more. So y equals to 3, it will mean that p of 3 will be q squared times p. You can also look at it this way as being a q times p, which means you failed the first time, you failed the second time, and then you were successful the third time. So therefore, this will give you the precise probability. Okay, so now notice or note this. If you sum all the probabilities, remember you're supposed to get 1, otherwise this is not a random variable. So here we go from y to infinity of q to the y minus 1 times p. This should give you 1. So let's see if that's the case. Here, since you're summing with respect to y, you can take the p out, so this will be p, the sum from y equals to 1 to infinity of q to the y minus 1. But remember that q is the same thing as just 1 minus p, so it will be the sum from y equals to 1 to infinity or 1 minus p to the y minus 1. Now, if you recall from pre-calculus, remember that the sum for a geometric series from n equals to 0 to infinity or r to the 0 was equals to just 1 minus r, assuming the absolute value of r is less than 1. Now here, since this is a probability, clearly this has to be less than 1. And notice that if you start at 1, then this will be give you 0. So technically you can just use this formula. So this will be p times 1 over 1 minus p, and this is equals to 1. So just check that. Okay. Now, finally, for this part, since this is a random variable, remember every random variable has a mean, and it has a expected value. So this is one of the terms, and the expected value of y is just going to be equals to 1 over p. You should verify that that's the case. You need a little bit of calculus to do it, but it's not that hard. And the variance of y is equals to 1 minus p over p squared. Now for this one, remember by definition, the expected value of y will be the sum from y times p of y, but p of y is equals to q to the y minus 1 times p. And once you do the sum, you have to take the derivative here to use on the series. You have to use technically this formula again at some point, and this will end up with 1 over p. Okay, so you should definitely check that. I think that's a homework problem. If not, we can go over this on the class. So this is a pretty good exercise, but just give it a try. So you just find this sum, it should give you exactly this. Okay. And then remember, you want to find this one. Well, by definition, this always equals to the expected value of y squared minus expected value of y squared, where this will be this value. And then to find this one, you just replace y by y squared in here. Okay. Okay, so now let's do an example. The example says the following: an oil prospector will drill a succession of holes in a given area to find a productive well. The probability that he is successful on a given trial is 0.2. So therefore, this is telling you that p is equals to 0.2. What is the probability that the third hole drill is the first one to be successful? Okay, so technically this is asking you how much is p of 3. So according to what we have, q, remember, is point A. So it will be q point A squared times 0.2, which again, this should technically be common sense. If you're successful on the third time, that means you failed the first time and you failed the second time. And by independence, you just multiply the 2. And whatever this is, that will be the answer. Okay, part B is asking the following: if the prospector can afford to drill at most 10 wells, so he can do 10 at the most, what's the probability that he will fail? So that means that he will fail every single time. Or in this case, that means that the first 10 were not productive or are not productive. So that will be just 0.8 to the 10 power. Now, part C says how many holes would the prospector expect to drill? So that's asking you to find mu, which remember is the expected value of y. For a geometric random variable is 1 over p. So in our case, it will be 1 over 0.2, which is equals to 5. So therefore, this means the fifth drill should be successful, or you expect it to be successful. Okay. We're going to skip section 3.6 and we're going to go to section 3.7, which is about a hypergeometric distribution. We actually haven't done this multiple times before, we just didn't call it a hypergeometric distribution. One of the examples we did was related to this. Let's say there was a company, and the company have 50 employees, and of those employees, let's say 5 were women, and you wanted to select, remember, I don't know, 9 people to, or 4 people to be laid off. Okay. Right, so in this particular case, this will be N. R will be phi, and the number you're selecting it will be N. So therefore, the probability that, let's say, 3 women are laid off, that will be the sample space. Remember, will be 50. Choose 4 because you're selecting 4 people. Then you have 5 women, and you want to select 3. So therefore, you have 45 left, and you need to select 1. So as you can see, we have done this before. It's just now we're making it more official. In this particular case, the value for y, then it will be 0, 1, 2, 3, and 4 after 4. So this one should start in 0. So there is a typo here. It should be 0, 1, 2, all the way to n. Now, since this is a random variable, obviously it needs to have a expected value and also a variance. And the expected value is equals to nr, n times r over capital N, and the variance is equals to n r over capital N and minus r over capital N, and capital N minus n, and n minus 1. This one is a lot more tricky to get, but it's not impossible. So I highly recommend you start memorizing the expected values and variances for all the random variables we're going to see, because that will make your life easier, and we'll be using it over and over and over. Okay, and the book calls all of these theorems for some reason. All right, so let's try an example from this section. So the example is the following. You have a box or an urn that has 10 marbles. Those 5 are green, 2 are blue, and 3 are red. So therefore, this is what we have so far. Capital N is equals to 10. Here, y is going to be the number of green marbles. And since you are selecting 3, so the value for n will be 3. And obviously the values for y will be 0, 1, 2, and 3. And r is equals to 5, because you have 5 green ones, so it will be r in this case. If you were talking about the blue, then that would change the values for r. So in our case, you want to find what's the probability that y is equals to 3. So according to the formula, this will be 5 choose 3, and then you have 5 left, but you want 0, and the value will be 10 choose 3. Alright, so let's look to another example that is a little more interesting than this one. Still using the same formula, but this requires also conditional expectations. The problem says the following: 5 cars are all at random and without replacement for a standard deco cars. Okay? What is the probability that the hand will contain all 4 aces if it is known? So if it is known, this means a conditional probability or given that it contains at least 3 aces already. All right, so here obviously n is 52 because you have 52 cars, and you are selecting 5, so lowercase n will be 5. And here, let's say y will be the number of aces, in hand. So therefore the question is asking what's the probability that y will be exactly equals to 4 given that you know that y is more than or equals to 3. So using the conditional probability formula, this will be the probability that y is equals to 4 and y is greater or equals to 3 divided by the probability that y is greater or equals to 3. What is the equals to 4 and more than or equals to 3 just implies y equals to 4 because that's the intersection, so it will be p of 4, and greater or equals to 3, this means 3 plus 4 because the maximum number of aces you have is 4. Now since y has a hypergeometric distribution, so for the top, probability of y equals to 4. It's going to be the following. You have 4 aces, you want 4. You have 48 cards left and you need 1. So all of this is going to be divided by 52, choose 5, because you are selecting 5 cards. Then on the bottom, at 3 and 4, it will be, this will be 4, choose 3, times 48, choose 2, divided by 52, choose 5, plus the 4, which is equals to this, which is the numerator. Okay. And then just use a calculator to simplify this beautiful thing. If you do everything, you should check this. You should verify this is equals to 0.0105. If this was a question on the test, this will be acceptable. Okay, you don't have to simplify it, you run out of time. The last distribution that we will be covering is the Poisson or fish distribution. So a random variable y is said to have a Poisson distribution if and only if it has the following mass function. There is a typo here. Let me just fix this part. So p of y should actually be equals to lambda to the y times e to the minus y, to e to the minus lambda divided by y factorial. And the value for y should go from 0 all the way to infinity. And here lambda, which is technically the expected value, has to be positive. Now the best way to look at y is the following. Y is technically the number of occurrences, okay, which will be lowercase y in a given interval of space or time. Okay. Now, since this is the density or mass function for this random variable, right, when you do the sum of everything, it should equals to 1. So this is a good exercise to check. So here it is. So if you add from 0 to infinity of lambda to the y, e to the minus lambda over y factorial, this should be equals to 1. Now to show that that's the case, recall from calculus 2, which I know it's been a while, but from calculus 2, you have the following, that e to the x is equals to the sum from n equals to 0 to infinity of x to the n over n factorial. Okay, so this is one of the last things you do in calculus. So therefore here, since the summation is with respect to y, you can take this one out. So this will be the sum from y equals to 0 to infinity, and the e to the minus lambda will go outside. And then here this will be lambda to the y over y factorial. So using this definition, well then this is technically e to the minus lambda, and all of this, it will be e to the lambda if you use this definition from calculus 2. So it will be e to the lambda, which is e to the 0, and is equals to 1. So clearly that's a random variable. Also, if you want to find the expected value, this is one of the variables where finding the expected value is one of the easiest thing to remember. Remember, the expected value by definition is equals to the sum from y equals to 0 to infinity of y times the density function, which in this case is lambda to the y times e to the minus lambda over y factorial. Recall that y factorial is the same thing as y times y minus 1 factorial, and the y's will cancel. So now you cannot have a negative factorial, so therefore you have to change the index. So now y has to go from 1 to infinity, and now you will have lambda to the y times e to the minus lambda, but now here you have y minus 1 factorial. So then we're going to use the classic math trick of multiplying by 1. So you multiply by 1, notice that this lambda can go in front. So then this will be lambda times the sum from y equals to 1 to infinity of lambda to the y minus 1 e to the minus lambda over y minus 1 factorial. Notice that since this is equals to 1, this one now will start in 0, and you can use this. Actually, you can use this, which you know that this is equals to 1. So therefore, this will be lambda times 1. So that implies that the expected value for y is equals to just lambda. Now this gets even more interesting because the variance of y, and you should check this, is actually also equals to lambda. So the Poisson distribution is the only one where the variance and the expected value are technically the same. Now here, using the notation, that means that mu is equals to lambda, and sigma squared is also equals to lambda. All right, so let's try one example. Cars arrive at a toll booth according to a Poisson process, so it's telling you that already, with mean 80 cars per hour. So here the intervals are very important, and you need to be careful with that. If the attendant makes a 1 minute, so now you go from 1 hour to 1 minute, so that means that lambda is going to be 80, because it's 80 per hour divided by 60. So this will give you 4/3 per minute. Okay. So what is the probability that at least one car arrives during the call? So therefore, at least one, remember, means y is greater or equals to 1. If we use the complement, it will be 1 minus the probability that y is equals to 0. So in our case, it will be 1 minus, if y is equals to 0, this will equals to e to the minus 4/3 times lambda, which is 4/3 to the 0 power, everything divided by 0 factorial. And once you do the math, this equals to 0.7364. Now, if we wanted to find what will be the probability that, let's say, exactly 4 cars arrive, then that will be the probability that y is equals to 4. So in this case, it will be e to the minus 4/3 times 4/3 to the 4 power divided by 4 factorial. And then just use the calculator. Okay, let's do one last problem from the Poisson distribution. So this is what the question says. Let y have a Poisson distribution with mean lambda. So find the expected value of this and then use it to show that the variance is lambda, which I have already told you that. All right, so remember, by definition, the expected value of y times y minus 1 is equals to the sum from y equals to 0 to infinity of y times y minus 1, and then the density function or mass function, which is lambda to the y e to the minus lambda over y factorial. Now we're going to do the same trick we did with when I find the expected value in the previous pages. So remember that y factorial can be broken down as y times y minus 1 and then y minus 2 factorial. Why are we doing that? Because this obviously will cancel this one and this will cancel that one. And now we have to change the index to start in 2 because you can have a negative factorial. So then instead of multiplying by lambda, we're going to multiply by lambda square and divide by lambda square, which again, you're just multiplying by 1. So therefore, this will be lambda square. So this lambda, you can take it out, and you can combine this lambda with this one. Okay, let me use a different color. Then you can combine this lambda with this one, and it will give you the following. Now this will be the sum from y equals to 2 to infinity, and this will be now lambda to the y minus 2 times e to the minus lambda divided by y minus 2 factorial. But this, all of this is equals to 1 by the definition of distribution. So this will be lambda times 1, which is just lambda square. Okay, so now notice the variance, one of the definitions we have, the variance of any random variable is equal to the expected value of y squared minus the expected value of y squared. So therefore, if you have the expected value of y times y minus 1, notice that that's equals to the expected value of y squared minus the expected value of y. So therefore, from here, it follows that the variance will be equals to the expected value of y times y minus 1, and then plus the expected value of y minus the expected value of y square of y, the whole thing square. But this one we just calculated to be lambda square. We know that expected value for the Poisson is just equals to lambda from the past. So this is equals to lambda, and then this is minus lambda square. So this will cancel, and from here you end up with just lambda as desired. That's it. All right, so this is it for section 3.8, and we are done with sections 3.6, 7, and 8.